Catherine, the electric potential energy that exists between 2 point charges? Oh, it's okay. Travis, when does she need to know by?
Fortnite.
No, it's actually a fortnight plus 2. It's okay. Tyler? Sierra?
QV. Right? Oh, no.
Oh, man.
Is it K? Yeah. K, Q1, Q2 over R.
This is the equation for the electric potential energy that exists between 2 point charges. We also have something which is delta V. When many of you wanted to drop the delta, I was unhappy with it. This stands for Matic what?
Electric potential difference.
Electric potential difference, not the change in velocity, but the electric potential difference. The general equation for the electric potential difference, Gary.
It is the delta U electric over Q.
It is the change in electric potential energy per unit charge. The electric potential difference that exists between a point infinitely far away and a point r distance from a point charge is Andrew. Who's got it for me? So KQ over R. You just combine these two equations. It's KQ over R. It's the electric potential difference between a point infinitely far away and a point r distance from a point charge. In other words, we can now use this to figure out the electric potential difference that figures out that it exists between a point infinitely far away and a point r distance from a continuous charge distribution. How are we going to do that? Vlad? Sure. I'm looking for how do we figure out the electric potential difference between a point infinitely far away and a point r distance from a point charge? I'm sorry, r distance from a continuous charge distribution. I said that wrong. I apologize. That's fine. Okay. Help them out. We're looking for the electric potential difference that exists between a point infinitely far away and a point r distance from a continuous charge distribution. Catherine?
Is it the integral?
We have the dV is equal to k dq over r. We split it into an infinitely large number of infinitesimally small charges dq. Therefore, the electric potential difference is going to be equal to the integral of k dq over r. We also have the electric potential difference in terms of the electric field. What is the electric potential difference in terms of the electric field, please? Hillary?
E over D.
I'm sorry, say again?
E over D.
No, but you have some of you have the letters correct, but not for the, anyway, it doesn't matter. And negative ED is true for a specific situation. It's true for what specific situation? It's not the general situation, Miller.
Constant electric field.
That's true for a constant electric field. I'm looking more for the general equation for the electric potential difference in terms of the electric field. Tyler?
Like integral E dot ds.
Integral of E dot, it doesn't really matter to E dot ds or E dot dr. I'm going to put the negative in there as well, just to remind you. Where is this equation on your equation sheet?
I don't think I tell you guys that it's a trick question.
It's on there. I want to know where it is.
Oh, it is.
Thumbs up.
Rearrange E equals negative dV over dr.
Notice it's they have the derivative instead of the integral on your equation sheet. 1 electron volt is equal to, okay.
I've honestly never known this.
Well, it's a good time to review it then. Hillary? Don't worry, if you forget, it's square. On the table of information. Jenkins?
1.6 times 10 to the negative 19th joules.
1 electron volt is actually a term for energy, not voltage. Capacitance. What is the equation, the definition for capacitance, please? Dorfstedt. Okay. We got to start finding more resources. The I don't know is no longer acceptable, Tyler.
Oh, Q over delta V.
Q over delta V, it is the charge that
So smart.
you can have per, that's right, you have resources. For example, something I handed out today. There were 9 handouts, so it might be hard to find. The capacitance, by definition, is the charge per electric potential difference. That's for a specific, or that's just a general equation. What is the capacitance for a parallel plate capacitor? Please. Emily. K E naught A over D. What is K in this equation, Stacey? No, it is not the Boltzmann's constant. It is the dielectric constant. Great. If we have 2 capacitors in series, the equation for 2 capacitors in series is, John?
One over C1 plus 1 over C2 is to the negative corresponding.
The inverse of the sum of the inverse of the capacitances. So when we have 2 capacitors in series, we know the electric potential difference across the battery is equal to, Tim?
V equals delta V 1 equals delta V 2.
When the capacitors are in series, the capacitances are the same. I don't know, that's what you said. I was just repeating what you said so everyone could hear it.
Yes.
Tim.
You add them.
What?
You add the delta.
You do.
You should change
What?
that.
Tim, what's going on?
When they are in series, the electric potential differences add. When they're in parallel, the electric potential differences are the same. The charges are the same. The charge on 1 and the charge on 2 are the same. When we have capacitors in parallel, we're going to have capacitance 1 plus capacitance 2, and the electric potential differences are the same. And the charges add. All right. The energy stored on a capacitor. We have 3 different equations for the energy stored on a capacitor. Sierra, give me all 3.
Q squared over 2C, 1/2 Q, 1/2 Q, change of V, and 1/2 C potential difference.
Great. We have all of the energies. We have 4 that are stored in a capacitor. The current. We have 2 different equations for current. Please give me one of the 2. Travis. The most common remembered one. What's the most common not remembered one, please? Nitish.
NQ drift velocity times K.
N is what, Loki? What is N? It's called the charge carrier density. What is Q, Jenkins?
It's the quantity times charge.
The charge per carrier. V, the drift velocity. You said V, the drift velocity. And A.
Cross-sectional area.
Great, the cross-sectional area. We now have an equation for electric potential difference in terms of current. What's the equation for electric potential difference in terms of current? Glenn.
We're going to have delta V equals, let's see, current.
Electric potential difference is just equal to current times the resistance. We then have resistance in terms of resistivity. What is the equation for resistance in terms of resistivity? Meg.
P, or if the rho,
what is the difference between resistance and resistivity? Match.
One of them's like material dependent. I don't know which one it is.
One of them is material dependent. Sarah Jane.
Resistivity.
Resistivity is the one that's the material dependence. Resistance is also dependent on material, but resistance is also dependent on Jenkins.
Length of
The shape, right? The overall geometry. So resistivity is a material property, whereas resistance is a property of a specific resistor. Why don't we pause for a few moments? Please enjoy a 1-minute decompression session. 3 equations for electric power. I put it back there. Eric, Matic, can you hand me my turn around?
The marker.
Marker, please. I am lost without it. Thank you. All right, we have 3 equations for electric power. Gary?
Current times the electric potential difference, that current squared times resistance, and that electric potential difference squared over resistance.
Dimensions for power, Mr. P. What is a watt, Meg?
Joules per second.
Joules per second. What is a joule, Jenkins?
It's like a Newton meter.
It is a Newton meter. What is a Newton? Travis. Kilograms times meters per second squared. What are the dimensions on the spring constant? Nick. Newtons per meter. Good. Well, that's fine. Okay. Let's see. EMF versus terminal voltage. What is the difference between EMF and terminal voltage, please? Vlad.
I didn't hear you. I don't remember right now.
That's okay. Travis has it for us.
One has like internal resistance and battery. One's ideal, one's
One is ideal, and one includes the internal resistance of the battery. Class, which one's the ideal one? EMF. Therefore, which one's always greater? Unless, and under what circumstances is the EMF equal to the terminal voltage? You can answer that? Many of you can. Clearly, if the current is equal to 0, the EMF equals the electric potential, the terminal voltage. Notice the terminal voltage is equal to the EMF minus the current times the internal resistance. Usually we use a lowercase r for the internal resistance. Therefore, if the current is equal to 0, the terminal voltage is equal to the EMF. If we have 2 resistors in parallel, notice the equations are reversed from what we have for capacitors. For 2 resistors in parallel, we get 1 over resistance 1 plus 1 over resistance 2 is to the -1 power. Again, the electric potential differences are going to be the same in parallel, and the currents are going to add in parallel. And for resistors in series, we are going to add them. Resistor 1 plus resistance 2, and the electric potential differences are going to add in series. And the currents are going to be the same in series. Kirchhoff's rules. Tyler, please spell Kirchhoff.
Kirchhoff.
Nice.
Yes.
Kirchhoff's rules. What are Kirchhoff's rules? How many of them actually are there first, Nick? Probably 3 is 1 too many. Probably 2. What are Kirchhoff's rules, Nick?
Delta V loop is equal to 0.
The electric potential difference around a loop is equal to 0, and
Net current in a junction is equal to net current out of a junction.
great. So let's say we have a circuit that looks like this. Let's do this one. Okay, we have EMF 1, EMF 2, resistor 1, resistor 2, and resistor 3. In order to use Kirchhoff's rules, what is going to be our next step? Winter.
We have
Draw what? Loops. We'll draw loops. We'll do loop A, loop B. We'll even do loop C around the outside as such. What else are we going to identify? Bill?
The direction of the current.
Directions of the currents. I'll just pick random directions for the currents. We'll have current 1, current 2, and current 3. We're now going to set up our, actually let's do the current one first. We'll do this as our junction. The current going in is equal to the current going out. Stasel, what are the currents going to be then? Great. We have current going in, which is current 1, is equal to currents going, I'm sorry. Would you like to try again? This one right here. Try again. Current 1 plus current 3 is equal to current 2, because both current 1 and current 3 are going into the junction and current 2 is going out of the junction. Let's do the electric potential difference around loop A, which is equal to 0. Please walk me all the way around that. Go ahead.
Oh, sorry. Delta V of T.
I'm going to call that EMF 1, because we have EMF rather than the terminal.
Okay.
Positive or negative?
That's positive. And then the next one is minus delta V resistance 1. And then you have minus E of 2. And then plus delta V 3.
Notice as we go from the negative to the positive terminal for a battery, we have a positive EMF. And if we go from the positive to the negative, we have a negative EMF. So that's why EMF 2 is negative. And if we're going in the direction of the current, the electric potential goes down. If we're going opposite direction of the electric potential, that's why the opposite direction of the current, the electric potential is going to go up. So we have 0 equals EMF 1 minus current 1 times resistance 1 minus EMF 2 plus current 3 times resistance 3. And then we have a potential difference around loop B, please. Sierra?
So, positive EMF 2 minus the potential difference of resistance resistor 2. Then positive plus. Subtract the potential difference of resistor 3.
Again, because we're going in the direction of the current there, so the electric potential is going to go down. So we have 0 equals EMF 2 minus the current through 2 times the resistance of 2 minus the current through 3 times the resistance of 3. So there you can see we have our 3 equations. You just need to rearrange them, create your matrix, use row reduced echelon form, use your calculator to solve that matrix, and you get your answer. Kirchhoff's rule. Generally, or I guess I'll say many times, we've seen just part of one of Kirchhoff's rules as a multiple choice problem, like just setting up this piece, for example, and figuring out an answer, just so you're aware that that's generally where Kirchhoff's rules come up on multiple choice. Let's see, we have an RC circuit. Just so you know, now that we've introduced inductance, sometimes students then ask, well, if we have an RC circuit, what's the inductance of the RC circuit? Well, assuming that, basically, unless otherwise identified, it is assumed that the inductance is going to be equal to 0, the self-inductance of a circuit. Yes,
On the AP test, we don't have to check our calculator, reduce row echelon form.
I don't think you have to, I would say, unless they ask you to, no.
So under final, we have to, or?
It's an AP test, so I would say no. Okay, RC circuit. Let's see. There are all sorts of things you need to know about an RC circuit. You have to be able to derive the charge as a function of time, the current as a function of time, and you should know the limits, both for charging and discharging. For example, what is the charge as a function of time? You should have this memorized. The charge as a function of time for an RC circuit if we are charging an RC circuit. Rensock.
Q2 equals the EMF times the capacitance times the quantity of 1 minus E to the negative T over RC.
This format is one we've seen many times. If you look in, I believe it was 2011 mechanics, you'll see that they actually had a mechanics problem where you end up having to derive an equation using this exact same concept, only rather it's not an RC circuit, but rather it was the force of drag, and you had to figure out the velocity as a function of time. It ended up working out, the derivation was almost identical to the way we've done it in an RC circuit. So this isn't something that you're only going to see on an RC circuit or an RL circuit. You might see it show up somewhere else as well. So be aware of that as well. You need to identify the limits. For example, if we're charging at time t is approximately equal to 0, what do we know about the current if we're charging an RC circuit? Glenn? The current is not equal to 0 at time is close to time t equals 0 for an RC circuit. What do we know about the current? Winter? It's a maximum. The current initial is at its maximum value. Over time, it's going to decrease such that, well, let's do this first. What do we know about the charge initial if we're charging an RC circuit? What's the charge initial, Meg? 0. Therefore, at time t is approximately equal to infinity, the current final, if you will, Vlad, is equal to? That's where it goes to 0. So it starts out at its maximum value and decreases throughout, and therefore the charge final ends at its charge maximum. So that is charging an RC circuit. You should walk through and remember the concept for discharging an RC circuit as well, and the limits. An ammeter. You place an ammeter in series or in parallel, Gary? In series. Why? Actually, let's do this. What is the resistance then of an ammeter, considering the fact that it is going to be placed in series? Dorfstetter, we know about the resistance of an ammeter. Bless you. Very, very small. So the resistance of an ammeter is very small. Because it's in series and you want to not change the circuit as much as possible. Therefore, a voltmeter you place in what, Winter? In parallel. And what about the resistance of a voltmeter? Very large. Again, because you're trying to not change the circuit as much as possible. All right, that brings us to magnetism. The magnetic force. We have the magnetic force on a moving charge in a magnetic field. Loki.
The force I had QV cross B.
QV cross B, or if you prefer QVB sine theta, depending on whether you're working with univectors or not. Which brings us to the right-hand rule. Please hold it up. Right hand. Class fingers point in the direction of. Curl the fingers in the direction of. Thumb points in the direction of. For a positive charge. The magnetic force for a positive charge. If it's a negative charge,
Use your left hand.
do not use your left hand. Do not use your left hand. It is in the opposite direction. We also have the force on a current carrying wire, which is IL cross B, or ILB sine theta. Let's see. We have the torque on a loop. I said that you should be able to derive it, and you should also have it memorized, and that still stands true. The torque on a current carrying loop in a constant magnetic field. What is the equation? I'll take a volunteer. Okay. IA cross B. I'm going to add an N at the beginning just because you gave it to me for one loop, but you could also have it for many loops. N would just be the number of loops. Or if you prefer NIAB sine theta. Let's see. Oh, we also have this equation, which I should identify. The magnetic force is equal to IL prime cross B. What is that? Why are we going to have an L prime? And
If like the wire's not straight, it's not a straight line distance.
okay, this is for a curved wire. This is the straight line distance from the beginning to the end of the wire, which means that the magnetic force, on a loop in a constant magnetic field class is equal to what? 0. Because L prime is equal to 0. So if you have a full loop in a constant magnetic field, the net force is going to be equal to 0. Does that mean the net torque is going to be equal to 0, class? No, it just means the net force is going to be equal to 0.